In this subsection, we're going to do even more with expected values, and we're going to be focusing on linear combinations of random variables. What I mean by that corresponds to what we've already seen before, and that is if I have a random variable x, let's say, and a and b are constants, then expected value of a times x plus b is equal to a times expected value of x plus b. And we went through an actual formal proof of that with respect to if x was a continuous random variable and working with the integrals. We saw why this was true. Now in this particular subsection, we're going to look at similar types of linear combinations of like this so that we can get a better idea of how to work with expected values. Some of this stuff we've actually kind of already put to use before, but I had not necessarily defined it yet. I find it's just better to kind of put all this in a subsection later on so that we can then examine it in detail. Let's next talk about a more general version of that one that we just saw. So let's say that g of x is any linear combination of constants with x. We can continue distributing that expectation through that linear combination. So for example, if g of x is equal to a times x squared plus b times x plus c minus d times x minus f, where a, b, c, d, f, I don't know why I didn't put an e there, but we have an f there, are all constants, and x is the random variable. Then what we can do is find then the expected value by pushing that expected value through the sum and also the corresponding minus signs. And we can then factor out then the corresponding constants, just like what we did for that special case of ax plus b. Now again, the expected value of a constant is that constant back, because it's like saying, what's the expected value of the number 5? Well, it's 5. It's not a random variable. Now, note that you cannot distribute an expectation through a product of the random variable itself, I should say. So, for example, expected value of x squared does not equal the expected value of x times the expected value of x, except in extremely odd situations that might occur, but in generality, it does not. Well, why? Well, simply write out what the expected value of x is. Expected value of x squared is. And so we see in this integral, if x was a continuous random variable, x squared times f of x. You cannot break that integral up into two different parts that looks at the integral of x times f of x dx times the integral of x times f of x dx, where we just simply broke up the x squared. You cannot do that. Just go back to your when you've taken a calculus class. You can't simplify an integral like that. Now, a more general version of this, I guess, point 2 there, we can talk about it with respect to 2 random variables, and you could extend this to 3, 4, and so on, but I think you'll get the idea with 2 random variables. Let's let x and y be 2 independent random variables, and let g of xy be a linear combination of constants with x and y. We can continue to distribute that expectation through the linear combination. So, for example, if this linear combination, it's a function of x and y, we denote it as g of xy, is equal to a times x squared plus b times y plus c plus d times x plus f plus x times y. We can again move that expectation through where you see those constants, where you see the sums, or if we had minus signs as well. So this expected value becomes a times the expected value of x squared plus b times expected value of y plus expected value of c. Of course, that would be just in the constant c, plus d times expected value of x. And for some reason, I don't have that there. Let me just edit that real quickly. Plus the expected value of f plus the expected value of x times y. Notice that I cannot break that x times y up because both are random variables. Now, there is a special case, though, where I could actually bring that expected value inside that xy part. And that is if the two random variables are independent. And that's what we're going to talk about next. Now, there is a special case where you do have equality, though. And that is if these two random variables are independent. Let's actually go through a formal proof of that. So here's my expected value of x times y. I integrate over all possible values of x and y, xy times f of xy dx dy. If I had independence, I can replace my f of xy with now the marginal PDF for x, denoted as g of x, and times the marginal PDF of y, denoted as h of y. Once I have that, remember that this g of x is only a function of x. H of y is only a function of y. So because of that, I can do some rearranging of terms inside this double integral. In fact, I can move this h of y outside of this integral with respect to x. And I could also just move that outside as well. And so what we have here then, if we take a look at this, is the expected value of y times expected value of x. And so thus, we have proved that under independence, we do have the simplification. But again, this only works if you have independence. Now, something kind of interesting happens with this then too. And that is if expected value of x times y is equal to expected value of x times expected value of y, look what happens when you subtract. You get 0. And when we do subtract these quantities, that corresponds to the covariance. And what did we say when the covariance was equal to 0? It's when you have independence. And so this is a nice little proof showing why that occurs. Also, the correlation coefficient rho sub xy then is also equal to 0 under independence. Now let's look at some expressions now with respect to the variance. Let's say I have a random variable x, two constants a and b. Let's say I want to find the variance of a times x plus b. Very often we will want to work with quantities such as this, and we need to derive a more simplified form for the variance. So it's only based upon x itself. And so let's go through an actual proof. So if I want to find the variance of a times x plus b, what that means is I want to find now the expected value of ax plus b minus the expected value of ax plus b, this whole quantity here, squared. Just to make sure you see this, let's say I just wanted to find the variance of x itself. Of course, then that's the expected value of x minus mu, or the expected value of x, squared. Notice the same format here. X, x. Ax plus b, ax plus b. Here is ax plus b. Mu is expected value of x. Okay. Now, once I have that, then I can use our previous expression that we've found that for the expected value of a times x plus b, which is a times the expected value of x, or in other words, mu, plus b. And look what happens. B disappears. And I'm left with a times x minus a mu, that whole quantity inside the expected value, squared. I can then move the a out because I have a as a common factor of both those terms. So now I have an a squared there. I have an x minus mu squared there. Let's continue factoring out a constant from the expected value. And I have a squared times expected value of x minus mu squared, which is the variance of x. So let's think about this. This is a nice little simplification. That the variance of a times x plus b is equal to a squared times the variance of x. B disappears. The constant gets factored out. That's multiplied by x. So it's always a good thing to remember how to find these variances quickly. Now let's extend this situation to where I have two random variables, x and y. And maybe I want to find the variance of a times x plus b times y, where again a and b are constants, x and y is random variables. One can show that, again, I factor out the constant that's being multiplied by the random variable. So I have a squared times the variance of x plus b squared times the variance of y. And notice I'm just adding these corresponding quantities together. But what you also get is this. We add 2 times a times b times the covariance of x, y. Remember, x and y could be dependent random variables. And because of that, that's why we have this extra term there. So to go through the proof, I want you to do it on your own. Go through the basic definition, what a variance represents. At some point, you're going to have an expression like this. And once you get to that expression, actually that will be fairly early on, I want you to actually multiply out the terms that are there. Okay. Now, if x and y are independent random variables, look what happens. That covariance part disappears. So the variance of a times x plus by is equal to a squared times the variance of x plus b squared times the variance of y. Let's look at an extremely simple example just to apply this, just to make sure you see this. So we can go back to the grades of the 2 courses example. Suppose for some reason we wanted to find the variance of x plus 2 times y. To do that, we would have 1 squared times the variance of x plus 2 squared times the variance of y plus 2 times what was a, what was b, 1 times 2, times the covariance of x and y. We have found these variances. We have found these covariances before, so we get 0.2931. 2 more parts here. So let's say that we have, let's say, n random variables, x1, x2, down to xn. And they have a joint PDF of f of x1 to f of let me say that, they have a joint PDF of f of x1, x2, down to xn. Suppose a1 through an are constants. Then applying what we just did with respect to 2 random variables, we could say that the variance of the linear combination of this sum of n different random variables, each with constants part of that sum, the a1, a2, down to an, being multiplied by each of the random variables, we can say that this sum is equal to we can say that this sum is equal to the sum from I equal 1 to n of ai squared times the variance of xi plus 2 times the sum for where I, that index is always less than j, of a sub I times a sub j times the covariance of xi xj. Okay, that might look kind of like you're not for sure where that comes from, but let's relate it back to what we had up here. Let me do some erasing. Okay, suppose x now is x1, suppose y is x2, b is a2, a is a1, and then that's what corresponds to the case of n is equal to 2 for that more general expression. Notice here we have x1, we have x2 here. Remember we had this 2 times a1, we had 2 times the sum for I less than j of ai, aj, covariance of xi, xj. Okay, for our particular case, we only have 2 indexes, 1 and 2. So for when 1 is less than 2, this sum is going to be equal to a1 times a2 times the covariance of x1, x2. That's how this, basically this longer expression, can be applied to this particular situation. on your own, if you're confused about this, try this case. The variance of a1 times x1 plus a2 times x2 plus a3 times x3. What that is going to be equal to is a1 squared times the variance of x1. I guess I'm actually going to essentially do part of it for you, plus a2 squared, times the variance of x2, plus a3 squared times the variance of x3. And then I'm running out of room, so let's go up here. Plus, now we have to deal with these covariance terms. Okay? So we have two generic indexes, I and j. What that basically means is we can look at the pair of 1 and 2, 1 and 3, and 2 and 3. So this would be 2 times a1, a2, the covariance of x1, x2, plus I'm going to do the same thing now for a1 and a3, and also a2 and a3, and the corresponding x's as well. Now, if all these random variables, x1 through xn, were independent of one another, look at the simplification. All the covariances are equal to 0. And now we have a nice little expression. We will use these results that you just see here for 8 and 9 later on when we look at some confidence intervals and hypothesis tests. I'll tell you what those are later on. But when we look at confidence intervals and hypothesis tests, we will use this result to derive some quantities that we need. So with that then that's just a little brief introduction into talking about expected values with respect to linear combinations of random variables.